Needless to say that I am happy to be here. In fact, Alec mentioned Hoffman's name, famous Hoffman lemma, if many people knows this. Alan once said, I'm happy to be anywhere. So I'm reaching the age where it's appropriate to say that I'm happy to be anywhere. Thank you, the organizers, for this wonderful, wonderful event. And it gives me an opportunity not only congratulate Boris with his 80th birthday, but to share with you some of my findings lately. And I'm very grateful to Alec for mentioning what he mentioned. Linear programming is a celebrated thing. Many of us make their living out of linear programming. This is some opinions about linear programming from Nobel laureates. You cannot argue with them. And sure enough, in '75, Kantorovich and Koopmans shared the Nobel Prize in Economics, and this is very important sentence, for their contribution to the theory of optimal allocation of limited resources. Very important sentence. And this is the three men, как сказать, отрешенные друг от друга individuals. Well, okay, so. Well, for 25 years in the United States, I asked everybody knowledgeable why Danzig didn't got the Nobel Prize. It would be extremely appropriate. And this is very strange. Nobody can explain it to me. Nobody. Even David Shannon, who knows everything, couldn't explain. Okay. Now, so this is something that everybody knows, that, and I want to give you some economic terminology to operate with. The C vector is the prices for the products. The X vector is how many pieces of each product will be produced. The A is the technological matrix which transforms the resources into products. And the B is the vector of given resources. Given resources. So what we want to do, we want to maximize the outcome of our economic activity. So we want to maximize the total cost of the products which we will produce within these resources. And sure enough, and this is what I didn't know for many, many years, I thought that the duality is due to Danzig, but it turns out that Danzig went to Princeton in 1947 to talk to John von Neumann, explain something about linear programming, and John von Neumann gave him a lecture, and as a result, he understood the duality. So always along with this problem, primal problem, there exists a dual problem. And the dual problem is, we want to, the lambda is the cost of one piece of the resources. Therefore, what we want to do, we want to minimize the total cost of the resources, but under the following conditions, that, you know, somebody will pay, the lambda has to be such that for every single product which we will produce, the cost of the column has to be at least as much as the Cj, which is the price of one piece of product on the market. It's like if I have the resources and I want to sell the resources to somebody, and I said, look, it's up to you. The price is up to you, okay? But you have to pay me not less that I will spend the cost of the column in the matrix A. So, and this is the beautiful theorem that, you know, the primal max is the dual mean and the so-called complementarity. What I want to emphasize is the C and the B has nothing to do with the X and the lambda. It means that the price for the products, okay, is not sensitive at all to how much we are producing. And the amount of the resources here is not sensitive at all to the fact how much we are paying for a piece. So I'm ready to pay, instead of $20, $100, nevertheless, I cannot hire anybody. Nonsense. But this is what it is. Now, so to be critical of linear programming is a sin, because it's a, but you know, I will sin now and pray later. So this is exactly what I said. And this is that probably I'm not the only one who knows this. And this is the example that, you know, if you change a little bit one of the coefficients, the solution completely different. So what can be done about this? And this is the subject of my talk. What we want to do is to make the price C sensitive to what we are producing. So the C is a function of X. So you have this map, you know, X to Cx, and the B is a function of lambda. If you are ready to pay more, you will get more, and vice versa. Now, what we are looking is, we are looking for such X star and lambda star that when you plug in the X star in the C and the lambda star in the B and solve the primal and dual linear programming problem, you end up with the same X star and lambda star. Fixed point. Okay. Fixed point has to exist. And this is the condition which I will make much weaker in the process. But I want you to understand what is this. This is a very, let's forget about vector functions. Consider this as a scalar function of a scalar argument. So what I'm talking about? What I'm talking about is this. If I increase a production of any product, the price has to go down. That's it. You produce more, the price goes down. And the margin, if you divide the right-hand side and the left-hand side on this, so you will have the Cx2, you will cancel this one dimension. You will have this ratio ratio, Cx2 minus Cx1, 2, and the sup of this margin has to be negative, and vice versa. Vice versa. What's happening here is if you pay more, you can buy more. That's it. Now, if the prices and the factors, resources, are well defined, then we are saying that this is satisfied this condition. So this is well defined. And if this is the case, then you have the equilibrium, the existence of the equilibrium, and you have these beautiful formulas which market clearance, if you produce, if the cost is more, okay, so if you have to spend more than you can make it, then there is no way to, doesn't make any sense to produce X. And also, if you are not using the resources too much, then the lambda is 0. So you have this theorem. Usually, to prove the existence, you need a Kakutani theorem. You cannot use it here because what's happened here is the actions is on the Cartesian product of the primal non-negative octant and the dual non-negative octant, so it's unbounded. But under the conditions which I mentioned, you can assume that you are in a very big ball in the primal and dual space, then you can use Kakutani theorem, and then you use these conditions to say that the ball makes no sense because it's inside of the ball. Now, what is this? This is a story which started 150 years ago. 150 years ago. So, if you fix the B, you end up with the so-called Walras-Wild equilibrium in a modern form. It's not, I'm not saying that Walras wrote this way. No. It was a lot of work. This form belonged to Kuhn, 1956. Now, and this is very important, very important. What we have now is, yes, Walras 150 years ago approximately said that C has to be sensitive to X, but B not. And this is a big difference. Now, if you use Kakutani theorem, etc., and the fixed point exists, then you have the, because this is a linear programming problem, then the dual lambda star exists, and you have complementarity, and this is due, obviously, to Kuhn, because it's 40 Kakutani, so it's 56. So now, next step after Walras made Wald after he escaped from Vienna, okay? But very unfortunately, he died in a plane crash. Walras itself was incredibly unhappy person. Now, why? And this is a very important lesson we have to learn. Very important lesson. And here is Nash. Turns out that Walras equilibrium is equivalent to Nash equilibrium in an n-person game. Now, this is I'm sorry. This is the payoff functions, and this is the the strategies. X is the strategy of the player Xi. And what's happening is Nash equilibrium is something that, if everybody accept the point X star, but somebody violate he can only lose. Now, and if you put together the gains, then you can write it in a very nice way, which is already similar to what we saw before. And what's happened is this, it's very important to understand what is happening here. We add up the gains, but the strategy of the I player is free. And he can pick any yi from omega, okay? Now, if we found the equilibrium, okay, then the normalized equilibrium, then there is no way for anybody to improve their gains. That's it. So the normalized is Nash. And we get involved with this long ago, published several papers in the 60s, early 70s. When he got the Nobel Prize Nash, I sent him these papers, and he sent me a letter saying that it's very strange. He couldn't expect that people in Russia can do this, even to be involved in this. Okay. Now, but the proof is, you know, due to Kakutani, and I spent already quite some, oh my goodness. So, you know, ladies and gentlemen, keeping in mind that I'm covering something which is 150 years old, maybe you will give me 5 extra minutes. You know. Yeah, well, okay. So Pavel was smart enough. He put me before the coffee break. Thank you, Pavel. Okay, so this is the two instruments. A little unusual. So what you are doing, you have F, phi, that, you know, X is fixed always, and you are playing with Y. So what you are changing is Y. Therefore, you have to get the gradient in Y, but at the point Y equal X, this is what we call pseudo-gradient. The Jacobian is more natural. This is the pseudo-Hessian. Okay. Now, if you write the optimality criteria for this using the pseudo-gradient, then it looks very usual, and this is nothing but variation inequality. Variation inequality. Now, you know, what is the relations? If you take phi as an integral of Ci when x's are fixed and t is running, then what's happened is if you have this condition, if you have these conditions, it's condition of the monotonicity of the derivative, it means that this function is concave in xi. And what it reflects is everything by the intellect is subordinate to the decreasing efficiency law. 1 shot of vodka is good enough. 2 shots is okay too, but then your enjoyment goes down. Efficiency law. Okay? Now, well, and it's completely equivalent, and therefore, you know, you can use, and we get involved because it looks very similar to convex optimization. We were crazy about convex optimization, so we were involved in this, and you know, we developed few methods, and then Boris and Bakushinsky come up with a general approach for variation inequality, which was very, very, very good. Now, this is the subject of my talk. This is the main thing. Now, you got this slide earlier. Now, look, assume that we solved already, and we have x star and lambda star, we have it already, then in order to find them, we know that this couple dual linear programming problems is equivalent to the saddle point of the corresponding Lagrangian. So let me write down the Lagrangian. And when you write down the Lagrangian and fix x and lambda, and the strategies right now is big X and big lambda is not a matrix, but the strategy is big and the fixed is what we have already, we end up with this saddle point. Now, but the saddle point is nothing but a two-person game when you do the machinery and do the normalized equilibrium, etc., and all of a sudden you have this pseudo-gradient J, and the pseudo-gradient J, which is this. This is the most important thing in my talk. It comes out very natural, very, very important. This is the vectors in which we will change the direction of x in the direction of lambda. Very, very important. So, and this is what I have to find. So, the pseudo-gradient, if each of them is monotone, then the pseudo strongly monotone, the pseudo-gradient strongly monotone. But in fact, I'm not going to use the strong monotonicity. I'm going to use only the strong monotonicity at the equilibrium, which means the following, that I'm asking the B and the C to be sensitive only at the equilibrium, okay? Now, if it is not sensitive at the equilibrium, then we are back to linear programming. It has to be sensitive. It doesn't make any sense. And this is what I'm asking. And if you have this, you will have this. And of course, Lipschitz, we will see the Lipschitz later. And then, you know, the operator, the variational inequality operator, this one, this is the condition number for the operator. And then, you know, we will use projection. So just a brief reminder that these two properties for projection is something that everybody knows. And what is the main point of this whole development is that I have to, my feasible set is Cartesian product of non-negative octant. So I have to project on non-negative. And this means nothing numerically. So you cut the negatives and that's it, and you're done. And this is the main point. This is the main point. Now, okay, so you have this and the projected pseudo-gradient. I take off my head. So, and this is the formula. Think about this formula. Think about this formula. Look, if you are making money, this is what you will get on the market, and this is what you spend in terms of resources. If you are making money, increase the xj. If you are losing money, decrease the xj. Now, if you have deficit of the B, I, deficit, this is bigger than this, sure, increase the price. If you have extra B, forget about it, the lambda doesn't mean anything, you know, reduce it. And what's happening? What is happening is this. This is nothing but the Euler method for this system. So I'm trying to make my point here because by taking Cx as a gradient of a quadratic concave function and Bx as a gradient of quadratic convex function, you can play with this system and see where is your trajectory heading. Where your trajectory is heading in terms of x and lambda. Okay. And this is something that the theorem, just wait, well, listen, you know, nobody will forgive me if I will stop here, okay? So, now, but if gamma is zero, then I cannot use and what I need to do is the extra pseudo gradient. I need to do the extra pseudo gradient. And this is due to Galya Karpilevich and many other people became very popular lately. And here's Galya. Galya Karpilevich is Boris' first wife. And little Misha, he's a professor at the Technion, my neighbor. If I need a nice cup of coffee, I knock his door. Now look what's happening. The same formulas, just 1 second. The same formulas, but with a predictor, which gets very popular after Ura's thing. And then you will have convergence, okay, if gamma is zero, but if gamma is not zero, you will have convergence with linear rate. And the most important thing is this, because the cost of this step is matrix by vector multiplication, it's only n squared, and the gamma goes from -2 to -1, which is very important. And I have to estimate Lipschitz constant. And then as a result of normalization, I'm losing substantial in the complexity. But if C in B is matrices, Cx is C multiplied by X, and B lambda is B multiplied by lambda, then I can do simultaneous normalization, and therefore I'm not losing the n. And this is the generalized Walras-Wald law, which include the cleaning. This is the cleaning of the market, and this is the beautiful symmetric formulas which characterize the Walras-Wald law. Thank you very much.